Hello everyone, and welcome to a new edition of the Joint Mathematics Colloquium, which, as guess you all know, it's a joint colloquium put forward by the four institutions that constitute ICMAT, CSIC, Universidad Carlos III de Madrid, Universidad Complutense de Madrid, and Universidad Autónoma de Madrid. I'm Julio de Vicente from Carlos III. I'm one of the organizers, together with José Ignacio Burgos from ICMAT, who's here, and José Conde and Pier Giulio Tempesta, who unfortunately cannot be here today. I'm going to give the floor to my colleague Fernando Lledó, who knows the speaker much better than I do, and he's going to introduce her. So please, Fernando.
Okay. Thank you very much. To put it short, Elizabeth Gillespie is one of those mathematicians that is able to put into relation very different fields of mathematics, graph theory, groups, groupoids, algebras of operators in Hilbert space, homotopy theory. She does also on K-theory. So I'm saying it straight from the beginning because she is visiting Carlos III and ICMAT in her sabbatical. So she's a very open researcher, so you may want to contact her because she's staying here until June, July this year. So please. Okay, so Elizabeth did her PhD at Dartmouth College in 2014. And it was during the PhD during her work on the PhD that she visited Carlos III and ICMAT, I think, for the first time, a visit that she is renewing now 10 years later, more or less. And yeah, she has participated in many activities done here in Madrid, different workshops, and she has been invited several times. And yeah, I will not read out the long list of her CV, just mention that she has written many articles, some of them alone and some of them with really relevant researchers in the field, Aidan Sims, for instance. And of course, she has published also in very relevant journals, Transactions of the AMS, International Mathematics Research Notices, Journal of Functional Analysis, etc., etc. If you are curious, she has a very good web page where you can take a look. And okay, let me just highlight two things that I find important. She is very committed to improvement of young researchers or getting into research of young researchers, and also very active supporting women research in mathematics. And she has done plenty of activities, workshops, schools, supporting these two items. Today she will speak about Williams conjecture and meteor graphs, and here you see again her expertise in these hybrid fields, directed graphs on one side, and algebras, I would say. Let's keep out the word C. I'm not sure if you're going to speak about C-star algebras, but it's really an example of how two different fields come together and behave are in a kind of symbiotic relationship. So Elizabeth, thank you very much for accepting, and welcome.
Well, thank you, Fernando, for the introduction. And yeah, it's a pleasure to be back at the Carlos III. As Fernando said, I was here during my PhD. I spent a year here at the Carlos III, and this is where I met my husband, actually. So it's a treat to be back. I'm going to tell you about Williams' conjecture for meteor graphs. This is work that I did with Luis Cordero, Daniel Gonçalves, and Ruzbeh Hazrat a year and a half ago or so. And it's been accepted for publication in the Israel Journal of Math, but it hasn't appeared yet, so the easiest place to find it is that archive link, if you're interested. Williams' conjecture is a conjecture in symbolic dynamics, which is an approach to studying dynamical systems. So I want to start by orienting us there. In dynamical systems, right, you're looking at the evolution of a system over time. And you might want to ask things like, over time, will the system eventually return to where you started? Or will you get, depending on where you start, can you get arbitrarily close to another configuration of the system? And does that depend on where you started, perhaps? And maybe just probabilistically, how likely are you to return to where you started? Or maybe to return near there? If we're talking probabilistically, right, the probability of a single event is almost certainly zero. Symbolic dynamics approaches these questions by discretizing both space and time. So instead of thinking about time as the real line, we'll think about time as the integer, sort of clicking on 1 click per second. And instead of thinking about all of our possible configurations as being some fuzzy space, we'll let the set of possible configurations of the system be some finite set or an alphabet. And so what we study in symbolic dynamics is shift spaces. And these are subsets of the set of sequences made up of that finite alphabet, by infinite sequences with entries from that finite alphabet of possible states of the system. But we don't want necessarily to allow all possible sequences, because we only want the sequences that are allowed under the dynamics, right? So you have the dynamics, this shift map, which if you feed it a sequence at point X in your shift space, it's going to tell you what's the next configuration of the system and the next configuration of the system. And so a shift space is some like collection of all allowable configurations under some dynamics. This is the set of sequences, so possible configurations over time. We're looking at time sort of all at once with the whole sequence, such that if you shift one sequence, one element of your shift space, you get another element of your shift space. You stay within this allowed configuration space. So that's a shift space, and we can actually make these into topological spaces, in fact metric spaces, by putting a metric on this set X of all allowed sequences on this shift space. We'll say that 2 points are close. The more points, the more sort of configurations that they share, the closer 2 points are. So if they share all of the configurations between -k and k in the integers, then the points are at distance at most 1/2 to the k. Now, one important question in many branches of math is, when are two things the same? When are they just dressed up in different clothes? And the concept of the same, or isomorphism, for shift spaces is conjugacy, which is, we've got topological spaces lying around, so it's an isomorphism in this category is a homeomorphism that intertwines the two shifts. So you might have, say, two different alphabets, A and B, and two different subsets of the sequences on A and B. Those would be your X and your Y. But you can put a metric on those, and then you can talk about a homeomorphism between X and Y, and you want it to intertwine with the shift maps. So that is symbolic dynamics. The particular sorts of shift spaces that I'm going to talk about today are these shifts of finite type. These are ones that are characterized by a finite list of forbidden words. And these are very handy to study because you can use matrices and directed graphs to study them. And so that gives you more tools, right? If you've spent much time with point set topology, you know that homeomorphism is a very hard question. We've maybe made it a little easier by restricting ourselves. We want homeomorphisms that intertwine the shift maps, but still, understanding conjugacy is challenging. And so if we have more tools, we're better off. Questions from the peanut gallery? No. Okay. All right. All right. So, for example, a shift of finite type. We've got an alphabet. In this case, let's make our life easy and say our alphabet has two symbols, 0 and 1. And our set of forbidden words, again, life is easy. Let's just have one forbidden word. We're not allowed to have two ones together. So then our shift space that we have associated to this is all of the allowed sequences of zeros and ones that never have two ones together. So in other words, you can have as many zeros as you like, and then you have a 1, but then you immediately have to have another 0. And I said shifts of finite type can also be studied via directed graphs. And so the way you do that is if you're given your shift of finite type, your alphabet and your list of forbidden words, let's make the vertices of the directed graph the allowable length n-1 words, and we'll put an edge from one vertex to another one if you can overlap those two vertices, those two words, and get an allowed length n word. So for example, with this setting, our forbidden length n words are all length 2. We've just got that one forbidden word. So our vertices are the length 1 words. In other words, the elements of the alphabet, the zeros and ones. So we've got two vertices. Now, I can go from 0 to 1 if I want, or I could go from 0 and stay at 0. So I have a loop at 0, and I have an edge from 0 to 1. At 1, do I have a loop? No loops, because I can't do a 1 and then a 1, but I can go from 1 back to 0. So that's my directed graph that's associated to this particular shift of finite type. Yes?
Sorry, so just to make sure I understand, shifts are in some sense more general than so if you're given a dynamical system that is set of orbits, which is a shift.
Yes. Yes, and so any shift I think comes as the set of orbits of a dynamical system, because you would say that the possible states of your dynamical system, that's your alphabet, and then you look at all of the possible configurations, and that gives you your set of allowed sequences, and that's your shift space. And so yes, I think that this is fully general. Of course. Okay. So really the shift space I said was the set of infinite sequences in the letters, right? So the graph encodes the set of infinite sequences, but really what's going on is there's infinite paths in the graph that are giving us our set of infinite sequences, our orbits of the dynamical system. So if you've got a directed graph, you get you have also its adjacency matrix. The number of entries, the VW entry of your adjacency matrix is just the number of edges from V to W. And I've allowed here entries in the natural numbers. Most of the time when somebody is drawing a directed graph, you might only draw one edge between vertices. And so then your matrices, or possibly 0, so then your matrices would be 0, 1 matrices. But it's important for some later computations, I'll come back to this point, that we allow multiple edges between vertices. So that's why we have possible entries in the integers, in the natural numbers. You could have 5 edges between the same two vertices if you wanted. Okay. But with this perspective, our shifts of finite type correspond with not just with directed graphs, but via the directed graph, via the adjacency matrix of the directed graph, we get matrices for our shifts of finite type. And this is relevant because of that question of when are two shifts of finite type conjugate, we can answer that in terms of the directed graph and in terms of the matrices. So this was done by Williams in a 73 paper in Annals. He showed that the two shift spaces for shifts of finite type are conjugate, so homeomorphic via a homeomorphism that intertwines the shift maps, precisely when the graphs can be turned one into the other by in and out splitting. And then there's a matrix characterization, which I'll tell you in a minute. But let's figure out what in and out splitting are. And this is where our need for multiple edges between vertices shows up. So, out splitting, I have been told by somebody very smart sitting in the front row that I'm supposed to just explain the bottom graph because it's just as clear as the top graph. So, if we want to outsplit at V, what we're going to do is we're going to take all the edges coming out of V and divide them into two groups. We will set one of those groups to be the edges coming out of V1, and the other group will be the edges coming out of V2. The edges coming into V, we will duplicate those. We'll put one copy going into V1 and one copy going into V2. So what happens here, let's say I want to split off this particular edge. So this edge is going to come out of V2, and all the other edges that come out of V, the one going back around the loop, and also this dotted edge, those I will say, and I'm sending those out of V1. The edges coming into V1, I've just got this one edge here on the circle, on the loop, and so I will send that in to V1 and also into V2. The effect here, because we just separated off this one edge, is to make this path coming out of V, essentially, it's a step longer now. And all the other paths along the cycle and the length of the cycle, we haven't changed that. But the top example is important for what I said earlier about we want to allow multiple edges between vertices. This one, the graph on the right here is the result of having done an outsplit at the red vertex there. I split up those two edges coming out to get one edge coming out of the top vertex and one edge coming out of the bottom vertex. And I duplicated the edges coming in. And so this graph here, this is a nice friendly graph with only at most one edge between any two vertices. But it is the outsplit of this graph, which has two edges between the same two vertices. So since outsplitting is important for understanding conjugacy, that means that at our graph level, we need to allow for sort of pre-outsplit graphs. Graphs like these, where there might be multiple edges between two vertices. So at the matrix level, we need to allow integer entries for integers larger than 1, not just zeros and 1 entries. Okay. Please. Oops, I'm sorry. I went way too fast. Oh, no, what did I do? Bah. Spoilers, indeed. Okay. This is going there, and then I won't cause any more trouble. Fernando, sorry.
So the idea is to make multiple edges simple. So that
Yes. Yeah, that's a good way to think about it, that when you're doing outsplitting or in-splitting, you're getting rid of these like higher entries in the matrix at the cost of making your matrix bigger. Okay. In-splitting is very much like outsplitting. In outsplitting, you send the edges that were going out, you divide those up among the two vertices, and you duplicate the edges coming in. With in-splitting, you divide up the edges coming in. Some of those going in will go one place, and some of them going in will go another place, and you duplicate the edges going out. But they're symmetric behavior. Okay. All right. Let's see. So what does outsplitting look like at the matrix level? Well, if we want to outsplit at V, I've only included symbols for the edges coming into and out of V, because outsplitting doesn't change anything else. So when I outsplit this, the graph associated to this matrix A, and I will get this matrix B for the new adjacency matrix, it's still going to have that A tilde. That's not going to change. But what's happened? When we split up V into two, V1 and V2, we have the same edges that were coming into V. This W1V up to WNV, all of those are going to go into V1 and into V2. The edges coming out of V, all of these, those are going to get divided up between V1 and V2. Some of them will go out of V1 and some of them will go out of V2. Now, here's a cool trick. So let's see, so I made this an n plus 1 by n plus 1 matrix here, and then this one is n plus 2 by n plus 2. So if I build this n plus 2 by n plus 1 matrix, S, by just ignoring this second column, it's not really telling me anything useful. And I let this R, this will be an n plus 1 by n plus 2 matrix. It's just a 1 and a bunch of zeros, and then next to it is the n plus 1 identity matrix. Now, if I multiply them, if I do S times R, I will get the outsplit adjacency matrix. And if I multiply them in the other order, I'll get the original adjacency matrix. And this idea of factoring your two adjacency matrices by the same things, by the same S and R, but in a different order, this underlies the matrix formulation of when two shifts of finite type are conjugate. Okay. The matrix R has n plus 1 rows and n plus 2 columns. The first column is a 1 and a bunch of zeros, and then it's the identity matrix. Yes.
So the first two columns are the same.
The first two columns are the same. Yes, exactly. Okay. All right. Unfortunately, just this sort of, well, I can factor A as SR, and then B can be factored as RS. That doesn't give us an equivalence relation on matrices. So what we have to do is we extend that, we turn it into a transitive relation, and we get this strong shift equivalence. And this was introduced by Williams in that 73 paper. So if A can be written as R1, S1, and then I write that in the other order, S1, R1, that's maybe not B, but I can factor it as something else, as R2, S2, and then I write that in the other order. S2, R2 could be factored in a different way, and so on, and I eventually get to B. Sn, Rn equals B. Then we say that A and B are strongly shift equivalent. And we saw just a minute ago that if your two matrices come, one is the outsplit of the other, then those matrices are strongly shift equivalent. And Williams' the first Williams theorem that I had on the slide was that outsplitting and insplitting characterize conjugacy of our shifts of finite type. And so it's perhaps now believable, that our shift spaces are conjugate if and only if the matrices are strongly shift equivalent. We take this relation that we saw for outsplitting and turn it into an equivalence relation. If and only if the graphs can be converted one into the other by doing insplits and outsplits. So this seems like we understand conjugacy pretty well, right? So why am I standing here giving you a talk about research I did 50 years after Williams proved this theorem? Because strong shift equivalence is really hard to verify. This is one example. There are other examples of pairs of 2 by 2 matrices that we do not know whether or not they're strong shift equivalent. Because there's no limit on the number of S's and R's that you might need to turn one into another. So Williams introduced this notion of shift equivalence which is decidable. There's an algorithm that will tell you whether two matrices are shift equivalent. And you can also compute it. You can compute shift equivalence via something called the dimension group of the shift of finite type, which turns out can also be described as the K-theory group of a C-star algebra, which is how I got into this whole mess. I did not grow up doing symbolic dynamics. I grew up doing C-star algebras, and so I started here, not with the Williams paper. So what is shift equivalence? We say that two matrices are shift equivalent if there exists an S and an R, so that factoring in alternate orders, we get some power of A and some power of B, and R conjugates A into B and S conjugates B into A. So it doesn't seem necessarily like it would be that much easier than the strong shift equivalence, but it is. And there are people that think that every talk should have a proof, so let me give you a proof. That if two matrices are strong shift equivalent, then they're shift equivalent. All right, so if A and B are strong shift equivalent, then we've got this sequence of S's and R's, right? A is equal to R1, S1, then you write in the other order and you keep flipping, and eventually B is equal to Sn times Rn. And we need to find matrices R and S so that S times R is equal to some power of A, and R times S is equal to some power of B, and these conjugate A and B. So let's take R to be Sn times Sn minus 1 down to S1, and let's compute. If I do R times A, then that's Sn down to S1 times R1 times S1. Now this S1 R1 can become R2 S2. And now I've got Sn down through S2 times R2 S2 S1. Oh, there's an S2 R2. I can turn that into an R3 S3. Now that S3 is next to that R3, and so on. We'll get to Sn times Rn times Sn minus 1 S2 S1, which is B times R. And then if we set S to be the other product, R1 up through R1, R2 up through Rn, then you can compute that A times S is equal to S times B. And if I multiply S times R, well then, let's see, so that's R1 up through Rn times Sn down through S1. Well, Rn Sn, that becomes Sn minus 1 times Rn minus 1. But now I've got an Rn minus 1, S minus 1, actually twice here in the middle. So that converts to an Sn minus 2, Rn minus 2, Sn minus 2, Rn minus 2. But because I had an Rn minus 2 over here and an Sn minus 2 over there, now there's 3 copies. Now I do it again, and there's 4, and I get down, just to An. And similarly, if you do R times S, you get Bn. So if I have strong shift equivalent matrices, then they are shift equivalent. Okay. Williams originally asserted in this 1973 Annals paper that shift equivalence actually was the same as strong shift equivalence. But he found a flaw in the proof a year later. And it turns out it's not just a flaw in the proof, there are counterexamples. Kim and Rausch came up with some in the 90s. All right. In 7x7 matrices. But still, shift equivalence is much more computable than strong shift equivalence, but strong shift equivalence is what gives us conjugacy. So we would like them to be the same. We would like to know situations where conjugacy is computable. And with Luis and Daniel and Roosbe, we found some. So these meteor graphs, which I will tell you what they are on the next slide, if you've got 2 graphs, one of them's a meteor graph, and the other one is shift equivalent to your meteor graph, then they're both actually meteor graphs. And if they're shift equivalent, then they're actually strong shift equivalent. So here, conjugacy, strong shift equivalence, is computable. All right. So what is a meteor graph? It's a connected essential graph with a unique source cycle and a unique sink cycle. So an essential graph is one where there's no sinks and no sources. And that's so that we can have that our space of infinite paths in the graph, two-sided infinite paths, is non-trivial, I guess, exists, right? You can always go backwards and forwards from any point on the graph. And we have a source cycle, so a cycle like this one that emits edges towards the other cycle but does not receive anything except from the cycle. And a sink cycle like this one that receives edges but does not emit anything except back into the cycle. So here I've drawn all of the edges sort of linking the two cycles as length 1. You could also have them be paths. You can have different lengths of cycles on the source cycle and the sink cycle, but that gives you some idea of what a meteor graph is. One might ask, why are these meteor graphs? Well, we were sort of thinking that there's sort of a bright head to it, the sink cycle. And it's got a tail, and I don't know. Meteor was much more catchy than lawnmower graph, which was the other idea. So, all right. So how do we prove that for meteor graphs, shift equivalence implies strong shift equivalence? Well, first we put the meteor graphs into a normal form using in and out splittings, which in and out splittings preserve strong shift equivalence. So that's fine for us. And then we use some number theory, Bézout's theorem, to describe which normal form meteor graphs are conjugate. Which ones can you get to via in-splitting and out-splitting? So this is still strong shift equivalence. On the shift equivalence side, it's known that shift equivalence is the same, as I said, as K-theory for C-star algebras, but also the same as something called the talented monoids, isomorphism of talented monoids. And so what we proved is that isomorphism of talented monoids occurs precisely when our characterization in point 2 holds. So we end up getting this nice invariant for both shift equivalence and strong shift equivalence of meteor graphs. Okay. So what is this talented monoid? This was introduced by my co-author Roosbeh, and the idea is you start with a graph, and the way I think about it is you want to collect the possible infinite paths in the graph, but sort of unrolling the graph somehow. You want to keep track of when you get to each vertex. So you take one copy of the vertices for each integer, and then we'll look at, we've got this relation that the copy of the vertex at level I is the same as you look at all the edges that start at that vertex V, their ranges at level I plus 1. So your graph at level I is the same as all the places you could get to at level I plus 1, and then is the same as all the places you could get to at level I plus 2. And this monoid, so this abelian semigroup with an identity, it keeps track of, this has a Z action, and so when we're talking about the talented monoid, we're talking about this monoid with the Z grading. Okay. And as I said, you can think about VI as the result of walking I steps forward from V0, from your original vertex in the graph. Okay. And Roosbeh proved with Huanghuan Li that, as I said, this talented monoid with the Z grading, it's isomorphic to the positive cone of the K-theory of the C-star algebra of the directed graph. And that's where I come into the question. For me, the K-theory of the C-star algebra is a much more comfortable place to live than these monoids. What are these monoids? But that I realize that is an unusual opinion here. Okay. So how am I doing on time? Yeah, all right. But let me tell you briefly at broad strokes what is K-theory for graph C-star algebras. Very broad strokes, but I'm happy to discuss more if anybody wants to learn more. C-star algebraic K-theory is what's called an extraordinary cohomology theory. So it's extraordinary because normally in a cohomology theory, you assign to each space or each C-star algebra Z many abelian groups, one for each integer. But in K-theory, K0 is isomorphic to K2, and K1 is isomorphic to K3, so we really only have 2 abelian groups to worry about. And so the long exact sequence that you get in cohomology becomes a 6-term exact sequence. K-theory can be very handy for studying C-star algebras because instead of trying to learn all the structure of a C-star algebra, which I haven't even told you what it is, you have to know about abelian groups, which at least we pretend we understand. Okay. So if I'm talking about the graph C-star algebra, if G is a graph, I can build a C-star algebra out of it, and the K-theory of that C-star algebra, you've gone the long way around Robin Hood's barn, but it's really computable from the adjacency matrix of the graph. K0 is the co-kernel of a map that comes from that adjacency matrix, and K1 is the kernel. Okay. So what is a graph C-star algebra? You start with your graph, which is vertices and edges, and those generate your C-star algebra. Your C-star algebra is a universal object for generators and relations. Well, what are the relations? The relations encode when 2 paths can be composed. When I can do an edge E and follow it by an edge F, then that means that in the C-star algebra, the product of E and F should be non-zero. And there's a lot of structure of graph C-star algebras that can be seen from the directed graph, not just the K-theory. Okay. Okay, and then I mentioned Krieger's theorem earlier that said that this shift equivalence is very computable. The matrices are shift equivalent if and only if, as ordered monoids, the positive cone of the K-theory of one graph is the same as the positive cone of the K-theory of the other graph. So shift equivalence is isomorphism of abelian groups. So, going back to the talented monoid, how did we prove that, how did we understand when 2 meteor graphs can have isomorphic talented monoids? Well, it has to do with the order ideal structure in this graded monoid. We have a unique non-trivial order ideal that comes from that sync cycle, the cycle on the right-hand side, that receives edges but does not spit any out. And then it's an ideal, so you can quotient by it, and that turns out to be a Z cyclic monoid that corresponds to the talented monoid at the source cycle. And so knowing this structure of the talented monoid, that it's very restrictive here, this was what enables us to prove that if 2 talented monoids are isomorphic, and one of them came from a meteor graph, then so did the other one. It also has to have this same structure of a unique order ideal that gives you the sync cycle, and when you quotient by that, you get another Z cyclic monoid. Okay. In fact, if 2 talented monoids for meteor graphs are isomorphic, the isomorphism is determined by a matrix like this, where we've got the identity here. This matrix here, this is it's reflecting a cycle of length, well, almost a cycle of length q, but having taken a few powers of that cycle, so that we're not it's not immediately the cycle, it's like the rth power of that cycle. And then this matrix B, this is the interesting part. This is encoding the number of edges from your source cycle to your sink cycle, the number of paths that you have from your source cycle to your sink cycle. Okay, and this matrix has to intertwine the adjacency matrices of your graph. And so that tells me what the structure of B has to be. And that turns out to be the same. So that characterization of B, that the structure that we have here, turns out to actually be the same as characterizing conjugacy or strong shift equivalence of the meteor graphs. So we proved that two meteor graphs are strongly shift equivalent if and only if their source and sink cycles have the same size, and perhaps up to rotation of one of the cycles, their normal forms look the same. And I'm not getting into what look the same means, but it agrees with the characterization of B that we had on the previous slide. Yes, so the source cycle and the sink cycle have, say, S1 vertices and S2 vertices. And so we would need that number of vertices for the source cycle and the sink cycle to be the same in both graphs, in G and G prime. So our proposition shows that strong shift equivalence really is the same as isomorphism of the talented monoids. But isomorphism of the talented monoids, that's shift equivalence. So for meteor graphs, shift equivalence and strong shift equivalence are the same. And that was what I wanted to tell you. So thank you much for listening.
Okay, Elizabeth, thank you very much. We have time for questions. We need to use the microphone because there are people behind the screen. So any question? Okay.
Thank you. So, is it possible to go back to dynamical systems and understand what is a meteor graph from the point of view of the dynamical system? I mean,
let's see. So here we go. So from the point of view of the dynamical system, once you're in the sink cycle, you can't leave, right? So if you're thinking about the set of infinite sequences that are infinite words in these graphs, they will all start here at the source cycle and then eventually transfer to the sink cycle and then continue there. So it's like you have a choice of timing, when do you transfer, and a little choice of how you transfer, but that's all the choice that you have.
So at the beginning we were talking about these dynamical systems that are given by a finite number of forbidden
words, yes.
And then this gives us a graph.
Yes.
Then if I go back and look at I take any graph, and I look at the infinite path in the graph, this is always of this type?
This is always of that type, yes. One way to see that is to think about the vertices of your graph. This is your alphabet, and the allowed length 2 words would be, all the edges from vertex V to vertex W, and the forbidden length 2 words would just be, if there's no edge from V to W, then that's a forbidden word. We never allow that. And so that's our shift of finite type.
Yeah, so when you moved from SSE to SE, you said, I'm aware informally that this is a more decidable problem. but then it made me think about decidability in the formal sense. Is it even know whether SSE is decidable?
It is not known whether it's decidable. That's this example that I had of the 2x2 matrices, that it's not known whether they are SSE or not. They're known to be shift equivalent. They're known to be SE, but there's no. It's open.
So we don't even know. And SE is decidable?
SE is decidable. That was proved in the 70s. Yes.
Okay.
Yeah, by Kim and Rausch, the same ones who later found the counter examples.
Okay. Thank you.
Yeah.
Okay, more questions? Maybe one. I have one. So you showed that for this class of graphs, you have the equivalence of SSE and SE. Are there obstructions, or are there other examples where you have equivalence, or is it completely open question?
Okay. There's some other examples where it's known. This is related. So when Rusbe introduced this talented monoid, he introduced it with the hope that it would indeed be talented at telling two different graphs apart, that two graphs would have isomorphic C-star algebras if and only if they have isomorphic talented monoids. And the talented monoid really encodes the shift equivalence. And there are other examples of graphs where it's known that Rusbe's conjecture holds. In particular, for comet graphs was one of the. So that's where you've got a cycle and then a bunch of edges coming in, and so. So there's other examples of classes of graphs where SE and SSE are known to hold. In terms of obstructions, I think that's I think that's a difficult question. It would mean sort of understanding, for example, those 2x2 matrices that I put up, understanding enough about why the structure of those associated graphs, why we can't figure it out there, and I haven't done that yet.
So more questions? If not, let's thank the speaker for the beautiful talk. Thank you.